Hello, good evening everyone. My name is Akhil. I am currently a PhD scholar in the Department of Mechanical Engineering at IIT Madras. So, am I audible to everyone? Okay, thank you. So, we'll be having this live sample problem solving sessions for the course Basics of Material Engineering every Tuesday from 7 to 8 pm till the end of the course. So I'll wait 5 more minutes so that anyone who is going to join will join, and then we'll begin the session. So in these sessions, I will show you some sample problems and then show the solving procedure also, so that you will be able to do better in your assignments and the exams as well. You can also ask any doubts if you have while solving your assignments or during the course also in these live sessions. Okay, I think we can begin the session now. Okay, people are still joining. I'll wait one more minute. Okay, it is 7:05. Let's begin the session. So, to those who joined late, my name is Akhil and I'm a PhD scholar from IIT Madras. So, I'll be conducting this live sample problem solving sessions for the course Basics of Material Engineering every week from Tuesday from 7 to 8 pm. In these sessions, what we'll be doing is I'll give some sample problems which are similar to the problems which you see in your assignments, and then show you how to solve them. Okay. So we also have today the professor for this course, Dr. Atnagavar Annavatla, is also in the meeting. So, and you can ask any questions if you have during these sessions, or you can post in the discussion forums also. So I think we can begin the session. So yeah. First question, we'll see about the ionic percentage in different types of molecular structures. So here it's given the electronegativity values for manganese and chlorine, and we are supposed to find out the percentage ionic character for MgCl2. So does any of you know how to estimate this ionic percentage? You can unmute yourself and speak. We have only 10-11 members, so we can have a detailed discussion way. You can raise your hand otherwise. Uday? Okay. Yes. Yeah, exactly. So is this what you are saying? Yes. So this is the actual formula how to estimate the percentage ionic character, and can you explain why this percentage comes into picture? Because we know the types of bonds are ionic bonds and covalent bonds. We have metallic bonds or hydrogen bonds or van der Waals based bonds. So why are we looking at percentage ionic character? So the reason why we are looking at percentage ionic character is because in reality the bonds are not perfectly ionic or perfectly covalent. In general, but there could be actually atoms or molecules which are perfectly ionic and perfectly covalent. So for the mixed cases where it's a mixed ionic covalent bond, in that case to characterize such a bonds we use this percentage ionic character, which is given by this formula. So for this case, if we do, so delta electron negativity is given by 3.0 minus 1.2, so it's 1.8. So the percentage ionic character is 1 minus e power minus 1.8 whole square by 4 into 100. So this turns out to be around 55%. So this way you can estimate the percentage ionic character if you know the electron negativity for any type of system. Okay. Yeah. So any questions for anyone, any doubts on this percentage ionic character? If you have any question, you can unmute yourself and you can ask. Yes? Yes, sir. Yes. Yeah. So it's this way, right? Or the opposite? Yeah, 0.25 into delta n square. That's not a problem. Yeah. Okay. Okay. So we can move on to the second question. So based on the number of people, I might change the procedure how we look at it from the coming sessions. Okay. So for today we'll be doing this way. I'll first ask the question and see if you are able to guess the answer. Okay. So the second question is regarding the crystal structures and all. So here we have what is the number of atoms per unit cell in a simple cubic structure. So can any of you explain this question? Try to answer this. Okay, so I hope all of you have watched the videos before attending these sessions or before trying to solve the assignments. I suggest all of you watch the videos. Uday, you are trying to say something? Yeah. Yes, exactly. So let's look at it in a general way. So if you have a corner atom in any structure, so if it is a cube and then corner atom, so it will be shared by 8 such unit cells. So the contribution from a corner atom would be 1 by 8. So if you have a face centered, yes, because each face is shared by 2 unit cells, so each contribution would be 1 by 2. So corner atoms are shared by 8 unit cells and face centered shared by 2 unit cells. And if you have a body centered, so it's not shared, only 1 unit cell will have it. So contribution from a body centered atom would be 1. So in this case it's given simple cubic. So simple cubic will have atoms at all the 8 corners. So 8 into 1 by 8, it will have 1. But what if it's FCC? Can any of you from this discussion say? It was not clear. Can you explain again? Yes, exactly. So because FCC will have atoms at 8 corners and in the centers of 6 faces. So from 6 faces we will have half contribution from each face, and then from 8 corners we will have 1 by 8. So the final would be 4. What about BCC in a similar way? Yeah. So 1 in the center and 8 corners. What about HCP then? Can any of you explain what would it be for Hcp system? Okay. So in HCP we will have at the corners, but each corner is shared by actually 6 atoms, 6 unit cells. So how many corners will it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 into shared by 6 unit cells, and you will have 2 face into 1 by 2, plus there would be 3 atoms inside, completely inside. So this would actually give 2 plus 1 plus 3, 6 atoms per unit cell. So simple cubic BCC and FCC you might have seen earlier in your +2 and all, but HCP is little complex, and the corners are actually shared by 6 unit cells rather than 8 for a cubic structure. So is this clear? How do you get for HCP also? Thank you. So does anyone have any doubts on getting the number of atoms per unit cell in any of these 4 structures? Okay, so I think we can proceed to the next question. Yeah, so this is little tricky. So what should be the A by R? A meaning the size side of an unit cell, and R being the radius of the atom. In an ideal case, what should be the relation between A and R for an FCC structure? So can any of you tell how can we proceed with these kind of questions? Here we are looking at FCC. Let's say if you have simple cubic or anything, how do we proceed? Why 1 by 2 root 2? So A square plus A square, yeah. So you are looking at the diagonal of a single face. So each side is A. This would be, if you are looking at the spheres, R, R and 2R. So A square plus A square should be 4R whole square. So 2A square should be 16 square. A equal to 2 root 2 R. Then what about simple cubic? Which I won't explain, I won't give you the final answer. But for simple cubic, what you should look at? Yeah. So in simple cubic, something of this sort you will get. So A square plus A square would be just a 2R whole square in simple cubic. So what about body centered? Here till now you are looking only at the faces, but if it is body centered, what should you look at? Yeah, but what are you looking at in body centered? Which diagonal are you looking at? Okay. Yes. So in BCC you should look at the main diagonal. So in that case, how will you get the diagonal's length in terms of R? In terms of R, it would be 4R only. But what should be these two terms? So you can think of it like this. First, you can get this diagonal, which is A square plus A square equal to some diagonal, let's say d square, d is equal to root 2a. And once you have this diagonal and this and the simple cubic root 2a, and then this is a. Okay, so 2a square plus a square is equal to 16r square. So 3a square is 16r square. So I see that only 2 or 3 people are interacting. If anyone has any doubts in this, you can also ask your questions. I hope this is clear. How do you get the relation between A and R for FCC, simple cubic and BCC? Yes, sir. Yes, sir. Yes, sir. Yeah. Yes, sir. Yes. Yeah. Sorry everyone for that mistake. Yeah. In simple cubic only it will be edge equal to side of the unit cell will be double the radius. So because in the diagonals they won't actually touch. Okay. Yeah. So does anyone know how to get a similar relation in HCP? In HCP, will we have only A or there would be something else? Anyone? Yeah? No problem. You can ask your questions. That we'll inform you later on. Sir, do you? Okay, let's proceed with the questions. Okay. Yes. Okay. So, can any of you explain how we'll do a similar thing in terms of A or R, and will HCP have any more extra thing instead of just A and R? So in HCP there will be one more extra dimension called C, which will determine the height of the HCP unit cell, and A will be the side. So in this case, to A and C are related to R. So how can you estimate A, C in terms of R? Or the ratio between A and C, just the ratio. So I will explain this. So in HCP, these three are the inside atoms, and this is the phase centers. So if you look at only this part, So you will be forming a tetrahedral. Yeah. With each side being A, and this being the C by 2, height of this tetrahedral being the C by 2. So this is the inside atom, and these are the so if you see any of these things, each is a triangle in a hexagonal face. So that triangle and one of the internal atom will form a 3-dimensional structure. So in that, if you see the height of that structure, that should be C by 2, and the edges will be A. So using this relation, we can actually see the relationship between A and C. So because there are two atoms on each edge, A should be 2R. Now to get the C, if you see the triangle, the projection of the C, direct projection, would be at the centroid for the triangle. So the location of the centroid would be 2/3 of the height of the triangle. So this distance comes from this, and the height is C by 2 as we have seen, and the hypotenuse should be A. So if you look in that sort, A square should be equal to C by 2 whole square plus A by root 3 whole square. So this way you can actually estimate C in terms of A. Okay, let's derive it. A square is equal to C square by 4 plus A square by 3. So 2A square by 3 is C square by 4. So C is equal to root over 8 by 3 into A. Okay, as you know A in terms of R, now you can also see C in terms of R, 2R into root 8 by 3. So this is how you can estimate all the dimensions of the unit cell in terms of the radius of the atoms for each structure. So is there any doubt in this estimation for HCP also? Okay, hopefully there is no doubt. So I'll repeat again. You have to look at the triangle formed by the edge and with one of the face center. So that triangle and one of the internal atom will form a tetrahedral, equilateral tetrahedral. So with that you can actually estimate the C in terms of A, and from there, because you know A in terms of R, you can estimate C also in terms of R. Okay. Any doubt in this for anyone? Okay, I hope there is no doubt. Okay. So the next question is estimating the density. Now we have seen dimensions in terms of the radius of the unit cell, and we have seen how many atoms per unit cell. So if you know these two, can we actually estimate the density knowing the atomic weight? So that is the next question. So can any of you tell me the formula to estimate the density? So how do we actually go about it, knowing the dimensions in terms of the radius of unit cell and knowing the atomic weight? average number of atoms into atomic weight. Yeah. So basically we have, let's say, 4 atoms in a simple, in some unit cell, some n number of atoms, and each atom has a weight A. So this is the total weight or total mass of the unit cell. So we know density is mass by volume. So mass of the unit cell, you can just say number of atoms. Number of atoms into the atomic weight of each atom. By volume of unit cell. So that would be, if it is a cubic unit cell, A cube, A being the side. Now here weight of each atom, you know the atomic weight. From that, each atom's weight would be atomic weight by Avogadro's number. So that's why you have this kind of formula for the density. Okay. So here the question is, what should be the density for an FCC with atomic weight given and the atomic radius is also given. So what will be the N for FCC, as we have seen earlier? Number of atoms per unit cell for FCC. Yeah. So, and what would be the volume for FCC? It is A cube. So we have seen A for the FCC as 2 root 2r. So the volume would be 2 root 2 whole cube into r cube. So if we put the corresponding this number, and we can take it as this 2 root 2 as m, so m cube r cube we can say. So rho would be n by m cube into area by r cube into Avogadro's number. So in this case, if we estimate now, given the values of 63.5 atomic weight and 1.28 angstroms, so rho would be 4 atoms per unit cell into atomic weight 63.5 gram per mole by Avogadro number 6.023 into 10 power 23, and then 2 root 2 whole cube into r cube, which is given as 1.28 angstroms. So 1.28 into 10 power minus 10 whole cube. So this way you can actually estimate the density for any kind of system, knowing the atomic weight and the crystal structure for that system. So even if you are given the atomic weights and radius and density, you can estimate what should be the n by m cube, and because you know what should be the n and m for each kind of unit cell, you can estimate the unit cell back. You can back calculate what should be the unit cell or crystal structure to have such kind of density. So is this clear? So similarly, these simple cubic will have n as 1 and a cube is 2r whole cube, and body centered cubic will have n as 2 and a cube being 4 by root 3, right? Yeah. 4 by root 3 r whole cube. So this way you can either go back, if you know the crystal structure, you can estimate the density, or if you know the density, knowing the atomic weight and the atom radius, you can estimate the what should be the crystal structure also. Okay, I hope this is clear. If anyone of you have any doubts, you can ask me in this question or whatever we have done till now. Okay. So I hope there are no doubts. Let's proceed to the next question. So here what should identify the invalid Bravais lattices. So can any of you explain what are Bravais lattices and how many there are? Anyone? Okay. So there are actually 14 Bravais lattices, and these are the 14 lattices in primitive, base-centered, body-centered, and face-centered. So base-centered here it means end-centered. So it means instead of on the all faces, it will have only on 2 faces. That is this base-centered. And face-centered all 6 faces, body-centered only in the center. Primitive being a simple cubic kind of structure. So based on the dimensions, since we are looking at the squares or cubes, so we have each of these dimensions A, B, C, and the angles, corresponding angles, alpha, beta, gamma. So based on this, we actually have these 14 combinations based on the location of the atoms also in that structure. So cubic, in that the primitive one is only on the corners, and body centered is inside the, and cubic face centered. So these 3 are what we are looking at till now. Perfect ideal structures where everything is equal and the dimensions are 90 degrees. But in reality, other cases are also possible. The dimensions does not have to be same, the unit cell dimensions. So those are these other structures. So if all the dimensions are equal, then it is cubic, and if the third dimension is different from the other 2 and the angle is 120, then it will be hexagonal. So this will be similar to the Hcp system which we are seeing. And rhombohedral, the angles are not 90, but the dimensions are equal. And in tetragonal, first 2 dimensions are equal and not equal to the third dimension, but the angles are all 90. So like this, based on the combinations, we will get these 14 crystal lattices. Now if you see triclinic Fcc, so in triclinic there is only primitive. The base-centered, body-centered, and face-centered are not available. Even if you try to make them, what usually turns out to be, one of these will actually belong to already existing systems. So that's why you don't need to consider them. These 14 would be the base structures. So triclinic Fcc is not valid. What about monoclinic BCC? That is also not valid. And tetragonal FCC, not valid. What about cubic FCC? It is valid. So is this clear regarding the crystal lattices? Okay. So I will move on to the next question. Yeah. So what kind of symmetries will these have? 2-fold, 3-fold, 4-fold. So when I say 4-fold symmetry, that means if you rotate about 90 degrees, if you get the exact similar shape from before, then 360 degrees by 90, which is 4, then it's called fourfold symmetry. But if you get a similar structure by rotation about 120 degrees, then it would be a threefold symmetry. But if you get it by rotation of 180 degrees, then it would be a twofold symmetry. So in this thing, monoclinic crystal system, what kind of symmetry will it have? So this is the monoclinic structure. The dimensions are not equal, but we have two angles to be 90 and third angle is not 90. So what should be what kind of symmetry it will have? So I'll give you like 2 minutes to think about it. So can any of you explain me now what kind of symmetry should this have? Okay, so I'll only explain. So this is beta, not equal angle, and these are 90, alpha and gamma. So if you take this system and if you rotate it by this axis, going through these two faces by 180 degrees. So basically you are rotating this line by 180 degrees. So if you rotate a line by 180 degrees, it will still be the same line because these two are 90 degrees. So once it rotates this line, so this point will go here and this point would go here and it would look exactly same. So this monoclinic structure has only one twofold symmetry. Okay, so this way you can actually look at each crystal structure and what kind of symmetries it has. So a cubic structure will actually have three fourfold axis symmetries. That's because if it is perfectly cubic, by whichever angle you rotate, by whichever in each of the three edge to edge faces, so if you can rotate any of those axis 90 degrees, you will exactly get the same structure again. So that's why cubic will have in each direction 3, and because you will get it by 90 degrees rotation, you will have fourfold axis symmetries. So like that, each crystal system has different folding symmetries. And triclinic, where no dimensions are equal and angles are not equal, doesn't have any symmetry. Okay. So is this also clear? These live problem sessions are supposed to be interactive, so if you have any doubt, you can ask. You don't have to feel any shy or anything. So can I move on to the next question? Okay. Yeah. So the next questions are regarding the Miller indices. Okay. So can any of you answer this question? What should be the Miller index representation of a face-centered atom in FCC? So we are talking about the position of a face-centered atom in FCC. So what will be the Miller index representation for the same? Uday, can you explain? Or anyone? Any of the face center atom. What should be the Miller index notation for that? So, are you guys familiar with Miller indices? Yeah. Will it be? Yeah, it can be, because any of the 6 phases, I didn't specify which phase it is. So one answer could be, you can look at this phase, phase at this phase. So for this, if you are seeing, the x component is 1 into, if that dimension is A, so the position is of that atom is 1 into A. And if you are looking at y, so it's at p by 2. And then if you are looking at c, so that is also at c by 2. So if you are talking about Miller indices, you don't have to specify this a, b, c. You will just say 1 by 2, 1 by 2. So this would be the position in Miller indices. So what are the other possibilities? You can also have 0, off. What else are possible? Yes, what else is possible? 1 off, this could be 1, and so these are the 6 face centered atoms and their positional indexes in Miller indices notation. So we can go a little bit more details. So in Miller index, you will have positions, vectors or directions, and planes. So if you are representing a position, you shouldn't put any brackets, just P, Q, R if they are P, Q, R. If it is a vector, so you will have to put square brackets, and if it is a plane, you will have normal parentheses. So if you look at different options in your questions or anywhere, so if you see without any brackets, any kind of brackets, then it is a positional Miller index. Or if it is in square brackets, then it is a vector, and if it is in normal parentheses, then it is a plane. So you should be careful. You can't use them interchangeably. Vectors is noted in this square brackets and planes are in this. And if it is a family of vectors, then it would be in these brackets. And if it is a family of planes, it will be in these brackets. So while you are specifying, or even if you are asked a question to specify the position, you should be extremely careful on the notations. Okay. So now we have written the positions for each of these phase. Yeah. Now let's look at direction. Let's say we want to write the direction for this position. What will be the vector for this Miller index position? So it's x of y1 z of. So this will correspond to this this face center. So what should be the vector notation? What should be the vector? So if you can see, vector will be from 0, 0 of the unit cell to this point. So the x component of that would be half, and y component being 1 and z component being half, as we know for the positions. But when you are giving the vectorial notation, you convert that to integer format only. So if you multiply all of these with 2, then it will become 1, 2, 1. So this would be the vector, Miller index vector for the same face centered atom, for this face centered atom. Okay. So is this clear? What about if we have this would be the Miller index vector. Any doubt in this? What? I didn't get you. Yeah. Sorry. Yeah. So for vector, square brackets, that's it. Now what if we are talking about this plane, Miller index for a plane? So if you are talking about planes, you should first look at the intercepts. So this plane is actually parallel to x-axis and parallel to z-axis and intercepting y at b. So it's parallel to x-axis, intersecting at b, and parallel to z-axis. That means it will never intersect z. So in this case, if you are mentioning the Miller indices for that plane, and this being 1, so reciprocal of this intercept, 1 by infinity, 1 by 1 and 1 by infinity. So 0, 1, 1, 0. So this is how you will specify this plane. Okay. So is this clear to everyone? How do you specify the plane, vector and index position using the Miller index representation? So using that, can you tell me what should be the Miller indices for this plane? For the plane given in this, highlighted in this blue. I'll give you 2-3 minutes to try to think about it. Okay, can any of you explain, or let's start together? So as for the plane, what should we consider first? Yeah, intercepts. So the x-intercept is A. What is the y-intercept? B by 2. And z it never intersects, so infinity. So the reciprocals, if you are looking, then it is 1, this is 2, this is 0. So the plane, is 1, 2, 0. So if you are looking at planes which are all similar, so can you tell me other plane which will be similar to this? let's say if you have one more plane here, so this is exactly same plane as this, so all this will belong to a single family of planes, you can say in that way. Okay, so is this clear how to get the position, vector and planes in Miller index representation? So for planes you just need to look at the intercepts and the reciprocals of that intercepts. For vectors you need to look at from where to where. If it's from 0 to this thing, you just need to get the positions, and then you need to look at the integers, not the fractionals. And in position you can have fractionals. Okay, so yeah, the question is now you know the plane index representation, we need to construct the plane. So how will you go about it? So we should go back reverse. So it's 2 bar, which means minus 2, 0 and 1. So the reciprocal of it is minus 1 by 2, reciprocal is infinity, reciprocal is 1. So it means it is parallel to y-axis, intersects z-axis at 1, intersect x-axis at minus half. So if you are plotting it, so intersects x-axis at minus half and parallel to y-axis, and then intersects z-axis at 1. So this point and intersecting z-axis at 1 and parallel to y-axis. So the plane would be so we will draw again. This being C and this being minus A by 2, and this is y parallel. So this is the plane. So I think now you should be able to go back from index to plane and plane to indexes. So is there any question in this Miller index notation till now? Okay. I request all of you to be more interactive sessions. They are like interactive sessions for you to learn more and should be able to answer assignments more. So, hello. Yeah. So the planes, how do you estimate these planes is based on the intercept, and then the notation is you take the so this plane, you are looking at the normal direction for the plane. This kind of represents the normal to the plane. Yes. Yes, that will give you the vectorial direction. Yes. The intercept parallel to y-axis, so it will never intersect the y-axis. So the next question, we have Miller index representation converted to Hcp based representation. So in HCPs, because we have C, 3 index notations is not that much useful. So we need to use 4 indices. So can any of you explain me how we can go from 3-dimensional Miller index to HCP based Miller index system? In Miller index we'll have 4 for Hcp system. So how these 4 are related to this 3 Miller indices? Okay, so U is related to P and Q, 1/3 of 2P minus Q and 1/3 of 2Q minus P and minus of U plus V, and W will be R directly. So this is how you can relate Miller indices in Hcp system to a cubic system. So let's say here we are given P and Q and R as 1, 1, 1. So that means the corresponding Hcp systems would be 1/3 into 2 minus 1, 1, 1/3 into 2 minus 1, 1, minus of 1/3 plus 1/3 and 1. So this would give 1/3 minus 2/3, 1. And because this is a direction, we should have integers. So if you multiply everything with 3, then this will become 1, 1 minus 2, 3, and the notation will be 1, 1, 2 bar 3. So is this clear? How to go from this 3-dimensional Miller index to Hcp Miller index system? So in Miller index, this 4 corresponds to actually in Hcp system. So this axis is A1, this axis is A2, and this axis is A3. So this UVT correspond to this 3 and W will correspond to the Z. So if you have a Miller dimension in terms of 1, 1, 1, you can convert that to Hcp's Miller index this way. So is this clear? Okay, I think for today this is it. So we'll have these sessions every week on Tuesday 7 to 8, and there is also one more session on Friday handled by one of my colleagues from IIT Bombay. Yeah. So I hope all of you will watch the videos before attending. It will be much more easier for you to learn. It will be a revision kind of thing. And from next week, I'll give you questionnaire, polls kind of questions. So you can plug in your answer and then we can discuss. This way I don't see the interaction more. Only 1 or 2 people are interacting. At least that way people who are not able to, maybe shy, can also interact with me. Okay, Uday, you are saying something? Yes, there will be 2 sessions every week actually, Friday and Tuesday. Yeah. So this is it. These videos and all will be uploaded in YouTube and will be shared with you the links. This document will also be shared with you. So in future, if you want to refer to, you can look at this document. And I request all of you to watch the lectures so that it will be easier for you to understand what's going on. Okay then. Thank you. You may log out now.